Systems 2, folks. It's time to push past your limits and learn some convolution. So I'm going to run through a few convolution examples for you. I'm going to try to make the video not super long. So the first example I'm going to run through is the one that was on my exam. So this is 3, this is 1, and this one is 2, and this is 1. So very quick, I'm going to go over what convolution is graphically. I know he hates when people learn convolution graphically, but it just kind of makes things so much easier to understand. So remember how he calls one will turn into tau and one will turn into t minus tau? Well, the t minus tau, what you're actually doing is flipping this graph over the y-axis. So it becomes, -1 with a height of 2 instead, or vice versa. You could do it with this side too. And then all you're doing really is dragging it through the other one, and you're figuring out what the total area accumulated is. That's essentially what the convolution, or the area, the function that's coming from mixing the two signals in this fashion, where you're dragging this one across. So that's essentially what you're trying to accomplish here. Mathematically, it's obviously a little bit more complicated, and don't know why he really does it this way, but he does. So this is going to be u of t minus u of t minus 3. And for those who aren't super strong on the step functions, u of t minus u t minus 1. So for those who aren't super strong on the step functions, if it's here, like your goal, like u of 0 is the standard like u of t step function, right? Like at u of t, it means that you're going up like this, right? And this value right here is at 0. So when you have something else like this right here, what you're actually doing is you need to set that equal to 0. And so when t equals 3, that's when this happens. Okay? So, and in this case, you're subtracting, right? So you're actually doing the opposite, where you're going down by 1. And similarly, if you want to go up to 2, just add a multiplier. You're going up by 2. So for this function, you're starting at 0, then you're starting at 0. You move up at the point, the x coordinate 0, or t coordinate. You move up to 2, and then you go back down. So without an axis there, this is what this function looks like, and this value is 1. So there's the 1, and yeah, it's not too complicated or too bad. Obviously, this is more of a signals and systems topic, but yeah. So let's move on to the actual math. So first things first, you have to do the thing where one of them just becomes a tau, and one of them is going to become a t minus tau. So in this circumstance, I did the t minus tau on this guy. It will work if you do it the other way. There's not really a right or wrong. With two rectangles like this, you can't really go wrong. So let's do that now. So the x of t will become the x of tau, which will become u of tau minus u tau minus 3. On this side, though, h of t minus tau is going to be equal to 2 times u of t minus tau minus u t minus tau minus 1. Okay? And now the idea is just to multiply them together and do the integration. So, and you guys have that formula or whatever. It's like the integral of h of t convolved with x of t, or however he makes it look. So this is what we're doing here. And so you first start with this, and so you're going to go an integral. Well, let's do this like this, because we're going to have to FOIL this equation out. U of tau minus u t tau minus 3 times 2 u of t minus tau minus times u t minus tau minus 1. Okay. So now, the first step you're going to have to do with this is FOIL this out, right? So, you got to do this thing. This is what I'm saying when I'm saying FOIL. Is first, outer, inner, last. It's just how I learned it. So, first things first, you're going to have, let's see, it's going to be 2 times everything. Because this is going to go, this is time, you got to technically distribute this 2. Right, so everything is going to be times 2, and based on the rules of integration, you can just pull that 2 out right away because it's a constant, right? So I'm just trying to make my own life easier in that regard. So you've got a 2 here, and then let's FOIL all this out. So you've got u of tau times u of t minus tau, and then second one is going to be minus u of tau, and then times u of t minus tau minus 1. Then the third function is going to be minus u of tau minus 3 times u of t minus tau. And then the fourth function is going to be plus u of tau minus 3 times u t minus tau minus 1. Okay. So that's just FOILing it all out. Now, the next step, the weird thing about integrating with u of t is it kind of doesn't really exist, if you will. It's just kind of defining a piecewise function. Piecewise being, where you do this little thing, y of t is equal to, and you got some value here for 0 is less than t, which is less than 6. Some value here, some value here. And, this goes from 6 to t to, greater than or equal to like 8 or something, right? So that's really what the u of t function is doing, is defining your piecewise function. So in terms of integration, I mean, the first thing you're going to want to do is say, okay, this right here is 0 plus, right? You turn on, you're at 1 at 0 plus. Here, let's go back to that. I'll do this, and let's go back to this t minus tau. So when does it turn into 0? Well, it'll turn into 0 and turn on, right? Like this up here, where you're getting that 0 value. So, So at that point is going to be, if you just literally just follow this equation right here, right? So t is equal to tau. So your limits for this integration is going to be 0 and t. And that's it. Because remember that tau is a dummy variable for integration. So everything here, like technically this whole thing here has a d tau. It just obviously got very long. But I can put that in here and here. So that's just establishing that right there, your limits of integration. Then again, this is just going to be a u of tau. And so I kind of just mentioned how it's kind of its own like dummy variable of integration, and then the u of tau doesn't really integrate cleanly, so it's its own little mess. But we're gonna get through it together. Let me move this to the side because this is gonna be a long thing of integration, so it's 2 times everything here. Now for this section, well, this is gonna be a 0 plus again, right? And this t minus tau minus 1 is equal to 0, right? So now, this time, if we want tau to be on one side, because that's going to be the limit of integration, we're going to get t minus 1. So this one is going to be minus 0, t minus 1. And again, this is because what you're really looking for is you want a tau to be here, or u of tau. And so, what do you put in here when you go from here? You're going to add in your t minus, this is going to become t minus 1 minus 0, is really what's going to happen. So yeah, so we can just put a u of tau here again. You can put d tau if you want. Now the next section, this section is going to be tau minus 3. Well, there's no t on this one, right? So if you go tau minus 3 is equal to 0, then tau is equal to 3. So the lower limit of integration is going to be 3. and this is going to be t minus tau, so this is going to be t. Fantastic. So now we can do that again. And then we can add the last limit of integration, which this is once again going to be 3. And this is going to be t minus 1, right? So t minus 1, this is going to be 3. All right. And then we can go back to the u of tau, d tau. Okay. So now let's put this all together. So this is kind of what I was saying. The way to integrate this is to kind of, like I said, it's almost like you're treating it like there's a tau there after the integration. So like it, you know, if you just have a u of t, it's almost like having just 1, right? Because that's, right? So you almost treat it like, okay, you had a, or I'm sorry, well, this is technically u of tau. So it almost is like treating it like you're just going to have 1 there. And so when you do the, you know, integral of 1 becomes tau, and then you'll do tau from t to 0. So, but then you have to keep in mind that you're still going to have a u of t when you're done, because this is like I said, defining the piecewise function. It's honestly, it's more confusing than it needs to be. The basic gist to remember is act like you have a 1 there, because that's what happens when you actually reach, you know, your 0 plus value. So act like you've got a 1 there, just make this a tau, and then just make sure to add the u of t for the same limits of integration that you were using. So in doing that right here, we're going to have t minus 0 times u of t is going to be what that integration comes out to. Now all of this is, remember, multiplied by 2. Then for the next step, we're subtracting, and this time it's going to be t minus 1 minus 0 u of t minus 1. And so I guess the key here is you're using the upper limit. Yeah, I mean, I guess that's the best way to think about this. You're using the total limits actually. Actually, yeah, you're still using like the whole limits. So think of this as like you could technically go t minus 0 here as well. This value minus this value is still going on in this u of t. So here you're still going t minus 1 minus 0, just like you did over here. Okay. Which this will just simplify to t minus 1. Then for this one, you're going to subtract t minus 3, and this is going to be u of t minus 3. Okay. And then plus plus t minus 1 minus 3. So this is t minus 1 minus 3 value, right? And then this is going to be the same, which is going to be t minus 4. Simplifying it to save some space. Yeah, and so that will end up being your total function. Like your total y of t function will be equal to 2t u of t minus t minus 1 u t minus 1 minus t minus 3 u of t minus 3. Oops, I forgot to add the 2 here. It's technically a 2t minus 2. And this is going to be a 2t minus 6. And then this is going to be a plus 2t plus 4 u t minus 4. All right. And so that right there, this, you don't need to actually do anything else to it. So if you actually follow through on the math, we can graph this first, and then I'll show you what I'm talking about. So the easiest way to describe this would be what is each section doing, right? Remember I said that this is a piecewise function. So at each different point, something is going to turn on. So we're going to treat it like 4 different parts. So this first part, you're going up by 2, starting at u of t, which is 0, right? So if we draw this graph, right? So starting at 0, we're going up by 2 per 1 second. And then our next, so I'm going to go, this is going to be from 0. Now this is going to continue until this part right here says from t minus 1, which is going to be, if we remember, from 1 is really what we're going to, right? Because we're going to the right. It's a minus in here. So that t minus 1 equals 0. T is equal to 1. So from t is equal to 1, this is going to be from t is equal to 3, and this is from t is equal to 4. Okay? So we can see everything that this is going to do, and really what you're focused on here, you see these constants. This is actually an 8, isn't it? See these constants? They're going to be factors for actually defining the function. Like if you really did all the math out for each section, and I'll show you that in a second, you can define how all of that works, or that those are just defining how all of it works. But the thing you want to notice is the rate of change, the t's, right? So at the very beginning, you're going up by 2, and you're only going from 0 to 1. So this is perfect, because now we know you're going to go up to 2, right? Here, you're now subtracting your minus 2t, so you're back down to nothing, right? And then at 3, you're subtracting another 2t. So now you're going back down until you get to this 4th mark, which then you are adding your 2t back, so we're back to 0. So that is what this convolution looks like, is this right here. This is going to be at 2. It's got and it's got changes at 1, 3, 0, 1, 3, and 4. So that's what this convolution looks like. Now, what I was saying initially was, like, if you plugged in 3.5, right? So if you plugged in 3.5, you know you've got a 2t here, but then you're subtracting this 2t, right? So these are going to wash out. You have a minus -2, so you've got a plus 2. Yeah, you've got a plus 2. I feel like this, oh, this is a minus, that's why. That's right there. I was going to say, I thought that these canceled each other out eventually, and they do. So you've got a 2t plus 2, or I should say you've got plus 2 from here, and then here you've got, yeah, so if you're doing at 3.5, so you've surpassed this amount. So at 3.5, 2 times 3.5 is 7, right? So you've got a -7. Now you've got a plus 2 and a plus 6. So plus 2 plus 6, because these constants didn't go away. Well, when you add all that together, you're going to get 1, right? Well, 3.5 being at 1 makes a whole lot of sense. If you started at 2 and you're down, you're going down at a rate of 2 per second, right? 2t. So at a rate of -2t, it kind of makes sense if you're going for 1/2, you get 1. So keep that in mind as you look at a function like this. These constants are there to help define your total function, but you really need to focus on the two t's, the rate of change. Now, if that was a little confusing, that's okay. I'll run through another one. And so this time, I'm going to be more focused on doing the actual convolution in the math. It's going to be quick. But this way we can apply what we just learned. So once again, we're going to do 2 rectangles. So I believe this one was like, what, a 2 and a 2? Yeah, 2, 2. And this one I did 1 and 4. Okay. So I started out by just doing the very basic, what are we defining these as? So we're going up to 2, so this whole thing is going to be multiplied by 2. We're still going up at 0, so that's u of t. And then we're going down at, u of t minus 2, right? Cool. And then on this side, we're going up at 0 again. So we've got and we're only going up to 1. So theoretically, you could also do like this, like everything is multiplied by 1. which I know is redundant, but it kind of gets the point across. U of t minus 4. If he gives you something stupid like a -1, like if he turned this graph around to look like this, I mean, none of this is anything crazy, right? Like if this was -4, it would just be u of t plus 4 minus u of t, right? Because instead of going up at 0, it's going down at 0, so that's where the negative would come in. And here it'd be going at plus 4, because don't forget, t plus 4 is equal to 0, t is equal to -4, right? So if he does something stupid to you guys like that, it's simple enough. Just, you know, follow the math. Nothing is overly complicated. Just, you know, follow the method, because that's kind of what he's going to expect you to do. Okay, so moving through that, so now let's do the convolution. So y of t is equal to integral of h of t, t minus tau. I'm hoping that I did the t minus tau on the h again. I did not. Okay, that's fine. So I can just do this then. H of tau times x of t minus tau. So that's your convolution. And so now let's define that function. So we've got 2u t minus tau minus 2, u t minus 2 minus tau. All of that multiplied by, and I mean, again, we see the 2 distributed here, so I will probably pull that out in a second. But u of tau minus u of tau minus 4. 4. And so we're going to FOIL again, nice and long. I'm just going to put the 2 in the front again, because it's going to be 2 times everything. When you know, this, that, this, and that, everything's going to be multiplied by 2. So we've got u of t minus tau, u of tau. I have minus 2u t minus tau times u tau minus 4. Oh, I put the 2 in there even though I pulled the 2's out already. Minus u of t minus 2 minus tau, u tau, plus u t minus 2 minus tau, u tau minus 4. Okay. And so now the next job is just to do this integration again. So I'm going to pull out the 2. I'm going to do this integration. Let's do the limits here. So for this limit is 0, right? This limit is t. This limit again is t. This limit is 4. This limit is t minus 2. This limit is 0. This limit is t minus 2. And this limit is 4. So noting that, let's actually do this in black, keep things separated. So you've got 0 to t, u of tau, minus integral, let's do that so that we know that the 2 goes to everything. This goes from 4 to t, u of tau, and this goes from 0, t minus 2. So actually take a note of this. Obviously, if this starts at 0 and ends at t minus 2, right? We got to keep in mind that this has a 0 lower. So it's probably going to be placed before this one, right? U of tau and plus integral 4 t minus 2 u of tau. U of tau. Everything technically has this d tau and stuff. I could just do that. D tau. I don't know that that's the correct notation, but you guys get what I'm getting at. So, okay. And so now we're going to do the same thing that we did before. So you've got 2 times everything. You've got a t minus 0 here, right, for the limits, u of t. Now here you've got a minus. Let's pull this guy over to here, so that we can keep these things in order. This is going to be t minus 2 minus 0, u of t minus 2. This is going to be over here. This is going to be minus t minus 4, u of t minus 4. And then this one over here, so I'm going to mark that real quick as well. And then this is going to be a plus t minus 2 minus 4, u of t minus 6. I can't quite, that looks bad. U of t minus 6. Okay. And so now we're looking at like basically the same function again, right? We've got all your little piecewise things here. And you just keep in mind that everything is multiplied by 2 and follow through on the math. So when t is, you're just hitting 0, right? So when you're just hitting 0, you're going to go up by 2t. Now for how long? Well, the next thing you have is a t equals to 2. T is equal to 2, pardon my English. So that means you're going to go all the way up to 4, right? Because you're going to go for 2, not just 1 this time. Okay, wonderful. Now, I guess that went up a little higher, but that's fine. So now you're going to keep going, and your next value, that's probably way too far, the next value is f4. Boom. Keep in mind you're subtracting here, and this is a single variable as well. Here you're subtracting again, so we're going to go down now at t minus 4 until we get to t minus 6, which is going to be there. And yeah, I mean it's that easy. And then after that you go back down to 0. And so again, if you follow through on the math on all this, it's just a matter of, is this on check? Is this on check? Is this on check? Right? Like, just remember to treat this as a piecewise function. That's essentially what your u of t's are doing. So just keep that in mind, and then yeah, if you want to follow the math through, you can. You can find another. You could probably find this value here, if you wanted to, etc. So that's another 2 rectangles convolution. So pretty much any 2 rectangles is going to create something like this, just from the nature of doing the convolution of those 2 together. I'm going to run through one more. If you want to stop watching the video now, you're more than welcome to. If you've got the gist of it, feel free to go back and try to re-understand if you need to. But the last one I wanted to do, just in case he decides to throw you a different type of curveball, right? I mentioned he could try to throw you a curveball where something happens before 0, but I don't think he will, because thinking about electricity, when are you going to have something happen before 0? Right? You're usually thinking about when you actually flip a switch. So rather than doing that, the other way you could do that, or the other thing that could happen, is it could be a different function. Convolution could be a whole lot of functions, but in this particular case, what if we had, for example, a ramp that then ended at 4. So you're starting at 0, you're ramping up. This is just a function of time, t. And for those who have not taken signals and systems, this is called a ramp function. It's a function of t. It's not typically something you want, because it's an exploding function. The pole is on the wrong side, but it's its own. We're talking about different type of stuff here. But this is known as in signals and systems as a ramp function. And then what if we convolved that with this function here, which is just another rectangle function like you've been doing. So first things first is to define our variables again. So if we're at 0 until we hit, oh man, it looked all nice, and then I ruined it. So if we're at 0 until we hit you know, the point t equals 0, and then we start going up, that means that our ramp function, which is just t, is going to be t u of t, right? And then we're going to go down at, let's see, minus, if we're at 4, so if we're at t equals 4, minus 4 u of t minus 4. Right? Yeah. So, that's what that function is going to look like mathematically. Now this function is going to be something we've already seen before. It's u of t minus u of t minus 2. Easy enough. Okay. So, now let's work out this math. I do not want to deal with turning this, I don't want to deal with that having a t minus tau. So I'm going to opt to make this the t minus tau function and call it a day rather than doing some crazy stuff. So this is going to turn into tau, u of tau minus 4, u of tau minus 4. Oops, minus 4. And over here, we're going to deal with u of t minus tau minus u t minus tau minus 2. Okay. Now let's do the same y of t. You know, and all these, I keep running out of room, but all of these, you know, they should be y of t is equal to, you know, make sure to do your labels. You know, Dr. Moreno, he'll mark you off for the stupidest thing. I'm running out of paper, obviously, or well, I guess it's not paper, you know, but you get what I'm saying. This y of t is equal to integral h of t minus tau times x of tau, x of tau d tau. So writing this whole thing out, you have, I'm just going to do the FOIL, like, because you're just multiplying these two equations, right? So I'm just going to do the FOIL. So I've got tau, u of tau, times u of t minus tau. And then I've got minus tau, u of tau, times u t minus tau minus 2. I'm going to make this a little closer together. I'm going to run out of space. Okay, then I'm going to subtract 4u t tau minus 4 u of t minus tau plus 4u of tau minus 4 u of t minus tau minus 2. Okay. Yeah, I think that's right. Yep. Okay. So, now we've got a couple things to deal with here, right? Obviously, this 4 we got to keep track of because it's not applied to everything this time, right? It wasn't in both parts. Like in this function right here, you had one part that had a t and one part that had a 4. It didn't all have the same thing. So we couldn't distribute this time and make it a constant of integration. But what we can do is we can still do a whole bunch of other definitions, limits. Let's go. So 0, this is still going to be t. This one right here is going to be 0. This is going to be t minus 2. This is going to be 4. This is going to be t. This is going to be, this is going to be 4. And this is going to be t minus 2. Okay. So, let's make our integrations. So now, remember how I said that your u of t is kind of just like a 1? Well, now you've got a tau, right? So you've got a tau here instead of a 1 where you're going from 0 to t. Here you've got a minus integral again. This is 0 to t minus 2 of a tau. You know, I should put the u of t still, u of tau. I should make this a little neater. Okay, and then you're going to subtract again, and it's going to be the integral of 4 to tau, or 4 to t. And there's no tau this time. Now we're back to u of t, right? And then this is going to be plus 4 to t minus 2. If I didn't mention this before, you almost always want your t's to be in the upper limits. There are exceptions to that, and it does depend on like which direction you're coming from. Again, if your time is, you know, if you're starting at 0 and you're always moving to the positive time, which is usually what you're going to deal with electricity, you pretty much always want your t's in the top. It wouldn't make much sense otherwise. I did forget to add that there is a 4 in both of these functions. Okay, so now we've got, you know, our 4 integrals, and the really only tricky part here, so all of this is equal to your y of t. The only tricky part here now is you got to deal with this, right? Which isn't really too bad. I mean, I told you to treat this like a 1 when you're trying to do the integration. But then the difference now is you have this right here. This that tau makes a difference, right? So the one nice thing about it is it kind of eliminates the need, you know, it's not a 1 which turns into a t, right? Now that you have the tau, that is going to help you with your limits of integration. Rather, I'm explaining it terribly. Let me just move on to the math. I'll show you what I'm talking about. So what is the integral of just, you know, tau? Well, it's going to be tau squared over 2, right? Now you plug in your limits. So rather than having to deal with like it being a 1 and turning into a t and then plugging in, you know, 1 minus 0, you're literally doing the exact same thing, but with, you know, because you're replacing your tau as the dummy variable integration, you know, here. So t squared over 2, or tau squared over 2 becomes t squared over 2 minus 0 squared over 2, right? You got to do both limits of the integration. But the nice thing is, of course, this turns into 0. So that's your first part. So let's do this y of t. Okay. And then just don't forget to add your limits in your piecewise portion with your step functions. This function right here. So this function would normally be tau squared over 2, right? So this is why I showed you the other part and why I've been kind of word vomiting about the limits of integration and such. You know, this is still going to be basically the same, but what's the difference? Plug in your limits of integration. Oops, t minus 2 squared over 2 minus 0 squared over 2. And so that's what you have to watch out for right there, especially in a function like this where you've got a ramp function, is just to keep in mind that you now need to add, you know, something like this into your function. So we can subtract this 0 right here. And the other thing I'm going to do before I plug it down here is I'm going to just FOIL this out. So this is going to be a minus t squared minus 4t minus 4 over 2. Make this a little nicer. U of t minus 2. Minus 0, right? Like that's technically what we're doing, is in this part right here is this part minus that part. So don't forget that we're technically doing that for both of these things. Obviously you're going to see that here in a second. This is nice and easy. It's the exact same thing we had before. You're treating the 4 and then the u of t is just like times a 1. So 4 with a limit of 4, I'm sorry, 4 is before that's before the integration. So this turns into like a 4 tau, and then with your limits of integration. So this is going to become minus, let's see, this is going to become 4t minus 16. That look right? Yeah, I think so. 4t minus 16, u of t minus 4. Okay? Now we're going to add the last piece. I'm going to draw it right down here because I'm out of space. This is going to be the same thing. This turns into a 4 tau after the integration from 4 to t minus 2. So this is now going to give you 4 times t minus 2 minus 16. And all of that times u of t minus 2 minus 4. Okay. So that's the gist of where we're at here. This is that function. I would probably recommend following through on some of this, some of the constants and such to make your life easier. But let's make an attack. Yeah, you know what? Let's just do that just to try to make our lives a little bit easier. So you've got a t squared over 2 u of t. This can be left alone. So it's going to be minus t squared minus 4t minus 4 over 2 u of t minus 2. Then this part right here. We distributed the 4 over here. So 4t minus, let's distribute this. 4t plus 16. Actually, we can't really do that because we need the u of t next to it. Apologies. Because of the u of t minus 4. But then let's distribute this 4 to make our lives easier. So this becomes plus 4t minus 8. So this should be minus 8 and then minus 16, right? So that'll be minus 24. U t minus 6. Okay. Now, theoretically, the constants should actually add up to 24 because when you get to, or no, actually, maybe not. Yeah, disregard. Sometimes the constants add up to their values. Like if we go back to this first one, you see the minus 2, minus 6, and these are both negative values, so this turns into plus 2, plus 6, minus 8. It's because you end up down here at 0, right? So when you finish, you want your final value to be 0 when everything is activated, but in this case, I'm not entirely sure that we're going to end up with a 0 function, right? So, or I should say a zeroed function. So this is going to be a little bit difficult to picture, but let's see if we can kind of analytically figure this out. So this is going to be pretty easy. So if we're starting at 0, right? Probably don't want it to be as large. So if we're starting at 0, you are going to notice that we're starting with just a t squared over 2. T squared would be essentially something like this, right? But it's going to be halved, so it's probably going to start a little lower, and then it's going to start building up, just because of the half function. Okay, so that's what it's going to start to look like. Now we're only going to go till we get to t minus 2, right? So let's just we can I'm guesstimating here. We're not going to quite get to the exact values. You can plug in if you really want to, but then the next part right here. So this t squared minus 4t minus 4. So you have another. If you guys aren't super aware, or if you guys aren't aware of this, you can technically break this up to like that's the same function as that right there. So you're subtracting your t squared over 2 already, and then you're also going to add. Well, I should say this function is this right here, but if you distribute this negative, you get a negative, a plus, and a plus. So this part right here, now you're just now it's linear, right? Now it's linear by 2t, and you're going to t minus 4. So whatever value you're at here, which theoretically we could actually calculate, right? So if you're at t squared over 2 until you hit 2 squared over 2, well, it's just going to be 2. So that means that at this point right here, you should actually be at 2, 2. That was just by plugging in. And so then at this point, at t equals 2, you're now going to turn this off, and now you're going to be going up linearly by 2t. Which means if you're going up to 4, because that's this value over here, 4, then that means you're going to end up at, what, 6? You're going to go up by 4. So I'm going to erase this. I'm hoping y'all wrote that part down. Oops. So this part is a 2t. So let's get up to 6. This part's going to go up linearly. And then we're going to move on to, at this t minus 4, we're going to subtract our 4t, which actually means, because we were at 2t, right? That's what was left over. So when we activate this, we're now going to go down. We're now at a negative 2t, right? So now we're going to go exactly the same curve until we get to the t minus 6. So actually, we should end up back at 2 if my math is correct. I mean, I think that's correct. So by 6, we should end up back at 2, right? And then from there, we're going to have, at this t minus 6, we gain back the 4t. So now we're going to go back up by 2t. And so that should be it. That's going to be the rest of this function is going to be going up linearly. Like theoretically at 8, you're going to get there. And it's just going to keep going. So that should be it. That should be the convolution of these two functions. I know that is a lot. I know that convolution is a lot. I'm hoping that this really helped y'all. Please, if you have questions, feel free to go annoy Sohaila. I know she'll love it. And yeah, once, you know, realistically, if you guys do have other questions, feel free to hit me up in the Discord or something. But yeah, I don't imagine he's going to hit you guys with any sort of ramp functions or something like that. But now you kind of understand, you know, with a regular integration, you're kind of just treating this like a 1. So when you get the integration, you know, it's t, right? Like the integral of 1, which gets you to t. And then it's just from your limits of 0 to t. So if you treat it like this, and then, you know, you just kind of add this back in because it's defining your piecewise function, these problems really aren't that complicated. And again, you're more looking at these than you are at this right here. But you know, I showed you, like with the 3.5, you know, you can go back in here and find, you know, the exact value by using this function. Just, you know, when you're, for the most part, you're looking for what is the t doing? What is the function of t doing? And so, you know, the t ramp did this thing where we had a function, you know, an exponential function, and then we went back to a linear function here, and then we went down, but then we went back up even. So definitely interesting how those two signals convolved. But yeah, all right, well, good luck, y'all.